Hello everyone, and welcome to my presentation titled Designing a Data Analytics Pipeline for Scalable Data Collection using AWS. In this project, I'll walk you through how I built a cloud-based data pipeline capable of handling large, varied datasets. My name is Raju Gura, and this work was completed as part of my coursework in cloud computing and data analytics. The main goal of this project was to design a robust, scalable data analytics pipeline for continuous data collection and processing. I used Amazon Web Services, or AWS, and key tools including S3, Glue, Redshift, RDS, and QuickSight to achieve this. Each of these components plays a vital role in data ingestion, transformation, storage, and visualization. Today, organizations collect data from multiple sources, but they often face challenges related to integration, real-time processing, and scalability. To address these problems, I designed a unified cloud-based pipeline that automates the ingestion, storage, processing, and analysis of structured and semi-structured data efficiently. My setup began with creating a secure AWS VPC that included appropriate security groups and subnets. I provisioned S3 buckets for raw data, RDS for structured storage, and AWS Glue for data movement and ETL operations. I also configured IAM roles to manage secure access and policies to govern the flow of data. I selected three types of data for this project: web traffic logs in JSON, CRM data in CSV, and social media feeds accessed through APIs. These were chosen based on their relevance to typical business needs, update frequency, and compatibility with cloud storage formats and analytics tools. I selected three types of data for this project: web traffic logs in JSON, CRM data in CSV, and social media feeds accessed through APIs. These were chosen based on their relevance to typical business needs, update frequency, and compatibility with cloud storage formats and analytics tools. I developed ETL scripts in Glue to handle common issues like null values, data type mismatches, and schema evolution. Automation was enhanced through AWS Lambda and step functions. For observability and troubleshooting, I used Amazon CloudWatch to monitor jobs and generate alerts when issues arose. I developed ETL scripts in Glue to handle common issues like null values, data type mismatches, and schema evolution. Automation was enhanced through AWS Lambda and step functions. For observability and troubleshooting, I used Amazon CloudWatch to monitor jobs and generate alerts when issues arose. My storage strategy was tiered for efficiency. Raw data resided in Amazon S3 due to its scalability and low cost. Processed data was stored in RDS and Redshift for optimized querying. For long-term archiving, I used Amazon S3 Glacier. IAM policies help secure access across all layers of the architecture. I created dashboards using AWS QuickSight, connected directly to Redshift and RDS. These included a real-time website traffic monitor, a lead conversion funnel, and CRM engagement trends. The dashboards made it easy for stakeholders to explore the data visually and draw actionable insights. Security and compliance were integral. I used IAM roles for controlled access, KMS for encryption at rest and in transit, and configured AWS config and CloudTrail for governance. CloudWatch logs and SNS were used to monitor and alert on suspicious or failed operations. This pipeline improved reporting times by 60%, empowered real-time decision-making through dashboards, and significantly reduced infrastructure costs. The pipeline also laid the groundwork for implementing predictive analytics, making it a strategic asset for any data-driven business. One major lesson was the importance of automation in ensuring data consistency and reducing manual errors. Schema consistency was crucial for stable reporting, and I learned that AWS Glue's flexibility and integration capabilities significantly reduced development time. Regular monitoring was also essential for maintaining performance and reliability. For future development, I recommend integrating Amazon SageMaker to apply machine learning models, adopting Amazon Kinesis for real-time streaming data, and expanding data sources to include third-party partners. These enhancements will further improve the pipeline's predictive power and versatility. My project was informed by AWS documentation and scholarly sources on big data architecture. These include a comparative study on Spark and Hadoop, and recent research on optimized IoT-enabled architectures for edge cloud computing. All references are listed here in APA format.